All right, we're back with another lesson. Today we're going to talk about a topic called inscribed angles. So we have some vocabulary or some new words that we're going to use in our lesson. The first one we're going to talk about is called an inscribed angle. So far in this unit we've talked about central angles, which are angles whose vertex is the center of the circle. An inscribed angle is an angle whose vertex is actually on the circle, right? And the sides are actually chords of the circle. So if we look over at this here, BC and AC are chords that intersect at a point on the circle, and that point is the vertex, and this ends up becoming the inscribed angle right here. And then if we go across the circle, the arc that kind of creates that, almost like the crust of a way, if you were to cut a pie in a weird way like this, the intercepted arc would be the crust, so to speak. To give you an analogy, so the intercepted arc would be here. And there's a relationship that we're going to talk about in a second about the arc and the angle. So the intercepted arc by definition then is the arc of the circle cut off by the two sides of an angle. So it's the edge of the circle between the sides, right? So that gives you a picture of it. So here's our theorem 11.9, which we're going to add to our theorem sheet. And the measure, so by definition again, when we see the word measure, we're thinking of degrees. So the measure, the degrees of an inscribed angle is half of the intercepted arc. So what that ends up meaning is this. If the arc is 100 degrees, right, for example, then the angle is going to be half of it. So it'd be 50, right? If the angle was 100, then the arc would be double it. The arc would then be 200. So we have a half and double relationship here with inscribed angles, and they're intercepted arcs. And just to go back, central angles have congruent arcs. So this is a little different than that, where everything was congruent. Now we have a half and double relationship. All right, so here's an example of some of the types of problems that we're going to see. So in this problem here, they give us this arc and this arc in this arc. They don't give us that. We could figure this out actually, because all of the circle has to add up to 360 degrees. So I'm actually going to do it a little bit differently just to kind of show you how we go about this. I'm going to start by finding x. And so if we look at this problem, x, right, is formed by the chord DG and GF. And that arc is there. So for these problems, I like the analogy of a baseball field because you have like the base paths and then like the outfield. And so it kind of gives you the stadium feel. And sometimes that might help you understand what part of the problem you're looking at. So if we look here, the degrees of this total is 150, all right? So if we look at the degrees, it's 150 degrees. And so based on the rule we just talked about a minute ago, if that's 150, then that angle has to be then half of it. So if we divide it by 2, we get 75 degrees. All right, the next part of the problem, I'm going to find this here. So I get an answer of 85. Well, how do I get it? Well, this 80, right? This 80 plus this 90 is 170, and they make up that inscribed angle. So if you divide it by 2, this inscribed angle will be 85 degrees, okay? So now we have two angles here, right? So the next thing is, if we look down here, we have what's called corollaries. And one of them says the opposite angles of a quadrilateral inscribed in a circle are supplementary. So if this is 85, this has to be supplementary to it. So this angle here is in fact going to be 95 degrees, right? Now it doesn't ask us to find angle E, but if we did, we now have 4 angles, and if we add them up, they should add up to 360 degrees. So because this is 75, this has to be supplementary. So if we subtract it, we would get an angle of 105. And if we add up those angles we get, they in fact add up to 360, which means that we are correct in our work here. All right, 2 other things. 2 inscribed angles that intercept the same arc are congruent. So what they're talking about is a problem like something like this, right? Where if you have an arc like this that is formed by that inscribed angle, and if you add, kind of connect it with this one, these 2 angles here are going to be congruent because they have the same intercepted arc. And because of that half double rule, we know that whatever the arc is, the angle will be half, right? And we can kind of move this around the circle, and as long as it touches those points, we know that's going to be, that rule will apply. So that's what that is saying right here. The next one here says an angle inscribed in a semicircle is a right triangle. And we're going to see that example on the next slide. All right. So in this example here, we're going to find the measure of each numbered angle. So I'm going to start with angle 1. So if we look at angle 1 here, we see that angle 1 actually forms, right, these chords form an intercepted arc that happens to be a semicircle. And so if we go back here, an angle inscribed in a semicircle is a right angle. So that tells us that this angle 1 has to be, in fact, 90 degrees. Okay, so again, based on this, we know that this has to be 90 degrees. If we look down here at angle 3, we see the same thing happen, right? That this, these two chords form this arc, and that is also a semicircle, so this angle has to be 90 as well. All right, so from there, we still need to find angle 2 and angle 3. And so if we look here, or sorry, angle 2 and 4, if we look here, they give us 60 and 80, and we see that this ends up creating angle 4, right? So we have 60 and 80, so that total is 140. And so how do we find the inscribed angle? We divide it by 2. So 140 divided by 2 will be 70. And then how do we find angle 2? Well, we know that the opposite angles of a quadrilateral inscribed in a circle, right? So if a quadrilateral is inside a circle, opposite angles are going to be supplementary. And so this angle will in fact be 110. And if you add up 90, 90, 70, and 110, you would end up with 360 degrees. All right, here's another one. So in this example here, this angle, right, creates this intercepted arc. And this arc happens to have a diameter that connects it. So this arc would in fact be a semicircle. So because it's a semicircle, we know that that angle has to be 90 degrees by the definition that we had, the rule we had a minute ago. Okay, so that one's pretty easy. All right, we have a couple other problems here where so far we've dealt with this, where we've had, you know, two chords cutting through. These are actually called secants, which we're going to talk about later, but essentially we have a chord where both of them are inside the circle. All right. We have some other different examples here where, you know, the chord is very small, right? And we have another chord that happens to be tangent as well. So we're going to see this, and what ends up happening here is that in all of these examples, okay, the point B and C is the same for all of these. Okay, so if you look carefully, B and C are placed in the same area. And what the example was doing was taking angle A and moving it around the circle, right? And as it moved it, it never changed the intercepted arc. So if it never changed the intercepted arc, what do we know about angle A in all four of these problems? Angle A is going to be the same. So that's part of that corollary that talked about having the same, you know, if it intersects the same points, that it's going to have the same inscribed angles. All right. Oh, coming back here, sorry. We need to find arc of this. So in order to do that, we need to find this angle, because this angle is the inscribed angle to that arc. And so if we do our 180 minus 90 minus 32, we get 58. And if we double it, we get 116. Okay. All right, let's try the last slide here for the lesson. All right. This says that if you have an angle formed by a tangent and a chord, it's half the measure of the intercepted arc. So it really doesn't change anything if you have a tangent line. So in this case, you know, if the line is tangent, right, whatever the arc is, you take half of it. It just looks a little bit different, and so for some reason students get confused. All right. Now if you go the other way, you still have the same chord, but now you're doing this arc formed by this tangent, because we see that the tangent went that way. It's really the arc going the other way. It's the same thing. So whatever this is, then we have this angle here, right? And we still have the half and double relationship that we've talked about. All right, so here's an example. This is going to get a little bit messy, so follow along and see how you do. So here they give us a central angle of 126. And they tell us that TU and SR are diameters. All right, it says line RB is tangent. Okay, so that's good to know because we're going to end up using this. So the first thing is the other central angle in the problem is 54 because 180 minus 126 is 54. So why is that important? Because that now is a central angle, and we know that this arc is going to be, in fact, 54 degrees, right? And if that arc is 54 degrees, the problem wants us to find angle BRT, which is here. So if the arc is 54, we'll divide that by 2 and get an inscribed angle of 27 degrees. All right, now to find TRS, okay, so just to clear this up, TRS is this angle right here. Okay? All right, so when we have all this, we know that since this is 126, this is also going to be 126, which makes this 126. So if we look at what we have, right, we have our inscribed angle and our intercepted arc. And so if we want to find out what that angle is, we just take half of the intercepted arc, which is going to be 63 degrees, right? And that is how you do problems with inscribed angles.